I think submarines are really interesting machines because of the amount of pressure that they have to experience while they're diving deep under the ocean. So let's suppose that we have a submarine with a couple windows on them. There's a top window and a side window. We probably need to find the force on the windows at a certain depth, but to do that, we first need to find pressure. And to do that, we're going to need some physics. So it's physics time, and we're pretty lucky because we have Mr. Einstein here to teach us some basic physics on fluid pressure and fluid force. We first have the equation P equals WH, which is used to find the pressure of the fluid at a certain depth. Here, W is the weight density of the liquid, and H is the depth of the liquid, and obviously P is the fluid pressure. And we also have the fluid force formula, which is F equals PA, but we can use some fancy schmancy substitution here and sort of plug in our equation for pressure from before into our force equation, and we get F equals WHA. And it's important to note here that A is the area of the object. We've seen W and H before. W is the fluid's weight density, and H is the depth, and P is the fluid pressure of the object. So let's use the physics formulas that we just learned to find the pressure and force exerted by the liquid or the ocean when our submarine is 130 feet under the surface of the ocean. Also, we know that our weight density of the surrounding seawater is 64 pounds per cubic foot. Plugging this into our pressure formula, we get that our window is experiencing 8,320 pounds per foot squared of pressure. And using our force formula, we can find that this equates to 249,600 pounds of force. So that means our window has to be really, really, really strong because it has to be able to withstand 249,600 pounds of force when it's 130 feet under the surface of the ocean. So we've found the pressure and the force that the horizontal window experiences when it's 130 feet under the ocean surface. But what about the vertical window? Our formulas don't really work with vertically submerged objects, and this is because vertically submerged objects have a pressure differential. The pressure of the object experiences changes as it goes deeper in the fluid, which means that the pressure at the bottom of the object is greater than the pressure at the top of the object. And since we're dealing with changing quantities, we need some calculus. So we have to use some calculus to derive an equation that we can use to find the force exerted by a fluid. And we start off a little conceptually by getting a object or a shape and then chopping it up into a ton of tiny rectangles. And then we can use our basic physics formulas that we learned earlier, F equals P times A, and find the force on just one of these tiny rectangles. And here, h of y sub I is just the depth of that one rectangle, and L of y sub I is the length of that rectangle, and delta y is just the thickness or the width of that rectangle. And notice how W times h of y sub I corresponds to P, or the pressure, and L of y sub I times delta y corresponds to the area. And now we can just divide our object into more tiny pieces of rectangles. To be specific, we can divide them into n rectangles, and we can use our summation formulas for that. Now, what we can do is take the limit as n approaches infinity. So that means that as we chop our object up into a million or a trillion or an infinite amount of rectangles, our approximation will get better and better. And we can sum all of the forces on each of those tiny rectangles up to get a better approximation. And finally, this equation that we have right now looks really similar to an integral, and we will put it into integral form, and we get f is equal to the integral from a to b of w, which is the weight density, h of y, which is the depth of the rectangles, L of y, which is the width of the rectangles, and dy, which is our differential. This looks like a lot of math, but honestly, it's really, really similar to the concepts that we can use to find Riemann sums or approximate integrals with Riemann sums. Confused? Yeah, me too. Let's go back to our submarine example and sort of try and apply them a little bit. So here's our problem. On the other side of the submarine, we have this vertically submerged triangular window. Find the force exerted on this window when it is 30 feet below the surface of the ocean. Also, it's important to note that the weight density of the seawater is 64 pounds per cubic foot. So we need a couple things if we want to solve this problem. Here's a diagram of our triangle, our window, and we need some dimensions here if we want to solve this problem. And let's say we've measured this triangular window and found that its base is 10 feet long and it has a height of 15 feet. Now all we need to do is find two equations, one for depth and one for length, and plug them into our force formula. That way we can evaluate our integral and get our answer. So let's find the depth first. I find that that's a little easier to do. We start off by creating the variable y, which is the height of any point in the space created by the triangle. Thus, given that our window is 30 feet under the ocean, our depth, or h of y, is 30 minus y. And this will make more sense once we see what's on the next slide. Because once we set things up, we basically have transformed our triangle onto the coordinate plane, where point A is on the coordinate location 0, 0, point B is on 515. We'll get to y later. And this sort of helps us visualize things a little easier, and will help us find the length later on. We also have included the line y equals 30, and that represents the surface of the water, like the top of the ocean. And we know this because, well, our window, as stated earlier, is 30 feet under the surface of the ocean. Now, here's a really important thing to note. It's that the y-axis is actually an axis of symmetry for the triangle, because if you notice, both sides of the triangle on either side of the y-axis is the same, or they look the same, right? And it actually splits the triangle up into half. And using this information and our known lengths, we know that point B is 515 because it has a height of 15 feet, the triangle. And basically, since the axis of symmetry over y sort of cuts the base in half, we get that that one length is 5. And that's how we get C is negative 515 and B is 515. And this will all help us find our equation for L of y. And using the fact that our triangle is split evenly by the y-axis, we can find twice the x distance between the y-axis and one leg of the triangle to find L of y. To visualize this a little better, let's look at this red line on this leg of the triangle right here. Once we find the equation of this line, we can solve that equation for x. And what that will do is that it will give us the distance between one leg and the y-axis for any point in y. So what we've done is we found the slope here, and we found the slope equals 3, and thus the equation of this red line is y equals 3x. Now, dividing by 3, we just get that x is equal to y over 3. And if we are given any y, we can now find the distance between that corresponding point in y between the line and the y-axis, and that'll help us find the length, or L of y, once we multiply that value by 2, which is why L of y equals 2x or 2y over 3. And now it's time to put this all together. We start off with our basic formula that we derived earlier, and then we plug in our values for w, so 64, h of y, which is 30 minus y, and L of y, which is 2y over 3. And plugging this into our calculator. Oh, also, before we do that, it's important to note that our upper and lower bounds for the interval is 0 and 15 because the height of the triangle is on the coordinate plane goes from 0 to 15. And now plugging this into our calculator, we get that the force of the triangular window is 96,000 pounds, which is pretty big. I mean, yeah, so the window, again, has to be really strong if it wants to survive all that water pressure and not break. Damn, you can apply this to the real world? Yeah, that's right, you can with dams. Here we have a picture of the Hoover Dam, and this dam is huge, and it has to go through various stresses from the water pressure. The Hoover Dam specifically has 350 feet of water stacked up against it. So when civil engineers are designing the dam, they have to use that force formula that we derived earlier to find out how much force a certain section of the dam must be able to withstand. And that's just for safety reasons. And also here is something I found cool, but this is a shape of a dam, like a little cross section of it, and you'll notice that it's actually made thicker at the bottom than it is at the top because there's a lot more pressure and force at the bottom. Can also be applied to aquariums. If you've ever seen an aquarium that's got these like huge glass walls almost, where there's a whole tank on the other side to display the fishes and aquatic life, you would know that that glass has to be really strong so that it withstands all the water pressure. And obviously, the water pressure changes as you go to the bottom. So, a designer or an architect or an engineer would have to be able to calculate the fluid pressure um, and force using the formulas that we learned about earlier to make sure that they buy or make the right type of glass so that the aquarium doesn't flood. And the whole takeaway from this is that a lot of water or any sort of fluid and a vertical object, most of the time it's glass, but it doesn't always have to be, you add those together and you just get a lot of applications of calculus. And that's basically it. Here are some of the sources that I used to learn more about this topic. And if you have any final questions, feel free to ask.